Welcome back. Our second speaker of the day is Huggett. He's going to talk about At the Edge of Spacetime, foundational issue in quantum gravity in the linear regime. Thanks a lot, Nick, for being here.
You're supposed to go a bit longer.
Nick is a distinguished professor at the University of Illinois in Chicago.
Okay, and hi everybody, I haven't said hi to yet. So, I've put the slides on Dropbox, so I encourage you to go to the, you'll have Annika send the Dropbox link, that you go to Dropbox and have the slides, so you can kind of refer back to them. I would encourage that. Okay. So, I'm going to start with a slide that just is sort of on the background to this discussion. I have found people tend to fixate on this background, which is not really what the talk is about. So try not to get too involved in this, but I'm sort of indicating where this is coming from. And what I'm doing is going to sort of point to a kind of corner of the book, the recent book with Chris, and some of the things we start to talk about there, and actually then start to talk about where I think these questions should go and the framework for dealing with them. So this is the background and relating it to past work, but that's not, it's the future-looking part that the talk is really about. So the book was about space-time emergence. So in general terms, I mean, how do you explain the appearance of classical spacetimes in a more fundamental theory of quantum gravity? Okay. And so, rush to the bookstore, go get a copy of this lovely book. If you don't like what's inside it, everybody likes what it looks like on the cover. You can frame that.
Judge by the cover.
Yeah, do judge this book. And the part I wrote that I kind of had primary responsibility for then was about string theory and the story about how string theory accounts for classical geometry. And this picture does not, why do I have to kick it twice every time? Okay. This picture does not sort of appear in the book, but it does sort of summarize about nearly 100 pages of the book. So this is a string, and what string theory says is actually, fundamentally the perturbative string theory says that there are strings, these one-dimensional objects, and they vibrate in certain ways, and one of the ways they vibrate, or the various different ways they vibrate, correspond to quanta of quantum fields, in particular of the graviton. And if you have, so you can go from strings to gravitons. So that's one part of the story. The part of the story that I'm looking at today is this part of the story. If you have many gravitons in a suitable state, then they start to look like a classical geometry. As you can see, this is the solution of GR here. So strings to gravitons to classical geometries, and this is the part that I'm talking about today. I want to sort of unpack that and suggest that there are some good questions there. So this is from Clifford Johnson's book on string theory, but kind of every textbook on string theory will develop this story and say something about it. The quotation from that book is, words and phrases which are offered include coherent state of gravitons, and these should invoke the idea that a star's gravitational field cannot be constructed using only the perturbative graviton picture. So this is exactly what's happening is, well, how do you form the gravitational field? Well, what is a coherent state? How do we get from here to here? So there's a story about that, and I'm going to kind of unpack some of the details. I think you can read into this quotation a little bit of skepticism or uncertainty about exactly how well developed that sort of story is. If you look at Polchinski, there's always, again, a sort of sense in which this is just Okay, this will take care of itself. And, nope, okay. That's what I want to, talk about now. What is a coherent state? What does it have to do with classical gravity? So, again, you can you'll see you can kind of forget that this came from thinking about string theory, because this question is common to whatever approach to quantum gravity you're taking, pretty much. Okay. So, what is this theory of gravitons and in which coherent states are constructed? So, people often just say linear gravity. You could say linear quantum gravity, but actually the procedure, as you'll see, is to linearize classical gravity and then quantize it. So I like this name. Also, LQG already it stands for something, so QLG can go the other way around. So here's a standard thing that most people who are working in quantum gravity, whether they're in string theory or loop quantum gravity or some other approach, would accept. So here's a way of doing low energy quantum gravity. So you start with a classical space-time and you perturb around it. And people will accept that this is a physically sensible procedure. This gives you actual physics of the world. And you should be thinking of this as whatever you think your more fundamental quantum gravity theory is, this is a low energy effective field theory for that. And that's quite common. This is a nice paper by Burgess. David Wallace kind of wrote a very similar paper like 20 years later. This is actually from a Nordita meeting. All the citations you'll find at the end, it's actually, there's a whole discussion there about whether this is really true, and it's pretty clear from the discussion that's there that this is what people think. So it's actually very nice. They talk about a lot of different things there. It's very nice. Anyway, so that's the sort of standard picture. Whatever's happening down here at the fundamental level, you can think, if you want to start doing quantum gravity, we have a theory for doing that. What is that theory? Well, as I said, you do linear gravity, so that means but that doesn't work, okay.
Yes. It works.
You have to direct it to the computer.
No, it's the pointer, like that'll go, but I don't
Okay.
see anything here.
No, I see it on. Or maybe it's so weak that I got it in my eyes.
I think people over there can see it, but I don't think you can see it at the sides. It's just for, yeah. Okay, so you take it, so this is just classical gravity, you pick a background, which I'll write with bars, and then you think there's going to be small perturbations around it. If they're small enough, you only need to worry about linear correction, so this is really the theory of gravitational waves. Well, here's an action that you can write down to describe this. I was at a talk the other day. I'm putting equations up not for you to follow them terribly carefully, but just sort of suggestive. And I saw someone doing this at a talk the other day, and they said, this is not an equation, it's a picture. And I kind of like that. I think that's quite a nice idea. But you can see, everywhere you see a bar, that's referring to the background. So we're going to take covariant derivatives with respect to that background, and that's the curvature. You see the h's, so that's the perturbations. So that's really what you want to take. And the other thing I'll draw your attention to is I put this lambda here, because we're going to talk about de Sitter space-time, so I want an equation that has a cosmological constant, so that I actually have a solution for that. Okay. Also, I gave this is coming from a talk that I thought Eric Curiel was going to be about, and I knew I needed to be a bit more careful about some things here, but it wasn't there. Okay, so that's the idea. This is not full general relativity. This is you just go to a linear order, and then sort of higher corrections you ignore because you think they're sort of quadratic in H, or well, there's already quadratic terms here, but sort of to get H, and so they can be neglected. Okay, when you've got this theory, you basically just have a field theory living in classical space-time, field theory for this H field, the perturbations, and then that's the thing that you quantize. And you can apply then standard quantum field theory methods. What this is the quanta of this field are massless, and they're, I don't know why I wrote this, they're spin 2. So ignore the one bit there, they're spin 2. And then they're living in this classical background, and that's basically the theory we're talking about. So that's what I want you to have a sort of picture of. Classical space-time with a quantum field for this H, and the quanta are gravitons, they're the chunks of gravity. This gravity in this picture is quantum. Okay, I've really quantized the H, and this is not then the same theory that often people call semi-classical gravity, where you think the gravitational field is classical all the way, you have quantum matter in it, so when you want to couple them, you have to take the expectation value for the quantum matter, stress energy, and couple that to gravity. That's not a theory in which gravity is treated classically. That's a theory quantum mechanically. That's a theory in which gravity is treated classically all the way through. So that's not the same theory. This phrase, semi-classical gravity, probably should be, in fact, the phrase semi-classical should probably be banned because it means just so many different things. Obviously, this is also semi-classical in the sense that half of the gravitational field is classical and half is, and then people will call this semi-classical gravity, but it's very different. Yeah?
Sorry, just so that to ensure to prevent me with 100% certainty, not understanding anything else that you say. So G mu nu bar on there, so G mu nu is the matter field plus the metric field plus the matter fields?
No, I've split up, so fixed some background, and then I'm kind of interested in geometries that are quite close to that.
Mm-hmm.
So the H is a perturbation of that, it's still geometry. Okay, but I want to sort of think about, I want to have the dynamics just for the fluctuations around this background. The fluctuations in the geometry. So H is still gravity.
But so the G mu nu, so this is, I mean that's the Einstein, that's from general relativity. G mu nu.
The sum is really from general. I'm doing general relativity is the whole thing.
G mu nu is just the metric.
G mu nu plus H mu nu is the metric.
G mu nu is a metric.
Yeah, but if I'm thinking about, but physically, if I'm thinking about the space-time, this sum is the metric. But I'm splitting it into a bit that I'm just going to leave fixed and a bit that has the dynamics. So the cases I'm going to look at, this is actually going to be Minkowski space-time. So you can think about it, what we're talking about here is I'm interested in space-time that are a little bit curved. And so I'm going to treat them by saying there's a background Minkowski and then I've got some small curvature I'm going to put on top of that.
Okay.
And that's the bit that I'm quantizing. And usually what this is doing, it's going to be a bit different in this case. If you're forgetting about the quantizing, usually what you're doing is you're wondering how this part will satisfy a wave equation, and so what you're doing is you're wondering how waves will propagate on some fixed background.
Mm-hmm. Okay.
No, good, that's okay. Yeah, that's pretty crucial. Does that make sense?
Yeah.
So, in terms of matter, there's no matter in here. I mean, there's this cosmological constant that's a bit matter-like, but
So
this is free. What I've written down here is a free field, and it's sourceless.
So G mu nu, but you could have matter fields in there.
And then we'd add some other terms to this as well. We'd have to have some T mu nu terms in here as well that told you what is that.
Okay.
Good. Keep asking questions like that if they come up, please, because that's I think very helpful. Yeah, that's fine. Yeah, okay. So, although this is widely accepted, it's not universally accepted, and famously, Penrose thinks you can have maybe a little bit of quantum in gravity, but as soon as even one graviton is created, the thing collapses and it stops being quantum. So this line of thought is an example of someone who does not accept this. There are versions of questions of background independence here. I'm going to flag some of these things and sort of come back to them. There's a question of background independence here. Once you start thinking in this way, you have the thought that, well, look, I could have picked a bit of a different G mu nu, and then I would have had, this is just a sum, and I could sort of shuffle, I could pick a different G mu nu, and then I just have to adjust this H a bit. They'd still add up to the same thing. I can shuffle back and forth between background and dynamics, and it should really be the same thing. And so this is an important notion of background independence that we talk about that we argue for in the book, in fact, that string theorists point to as well when they're told that the theory is not background independent. That's the sense in which they say there's a sort of implicit argument that it is background independent. So, yes.
Yeah, if it's too much, just I mean, we can talk about it in a Q&A, but on this question of background independence that you were just talking about, is how much of a change you can make in the split between metric and perturbation? Is this like a perturbatively small one, or can you just, as long as you keep the sum?
Let's come to that. So yeah, I'm just flagging that question, sort of for now. That's exactly the right kind of question you want to have here. What kind of changes can you make to that split, if any? Okay. And I said this was a low energy effective field theory, and the way to think about this then is what's going on is there's this underlying theory. This G mu nu is some possible classical, quasi-classical solution to that, and then I want to see the small quantum effects that are kind of coming out that then would sort of accrue around there if I start taking account more of the quantum gravity. Okay, so that's the general picture, and so that's what I'm talking about, and that's that second step in the string theory derivation. And it's quite interesting when you go to the literature. In some sense, the things that are said here, you get this from the Johnson quote, are just sort of standard law in quantum field theory, but it's actually hard when you go into the literature to distinguish things that really have been shown, things that don't need to be shown because they're so obviously true, and then things that they kind of obviously just sort of hoping are true, and so some of the project is to try to straighten those things out. This is very much to do with you can see with this sort of classical limit. There's important stuff here, but it doesn't get included in textbooks very much, so things are sort of diffuse when you're trying to trace all this down. So, I've just said the theory. I need to say something about the classical limit. So, I should have left that up, but you're all following it on in the slides that I gave you on the blackboard, so it's okay. What I want to talk about is how to construct classical solutions within that quantized linear gravity framework, so that we're back in the sort of classical picture. The quantum bits now look like classical corrections to the background space-time, so that the total is a classical, quasi-classical space-time. We're going to look at this done for de Sitter space-time and for Newtonian space-time, in Minkowski space, in a Minkowski background. And so we need to understand how, in quantum field theory in general, classical fields are to be understood. And here the notion is the one that Johnson said, which is that of a coherent state. So, I'll talk about coherent states. We'll do it in the particle case because it's actually pretty intuitive there. And then I'll just sort of gesture at fields and say it's basically very similar by analogy. So when we do quantum mechanics, the standard reasoning is we have classical variables, position and momentum. We impose commutation relations on them. Here's the sort of the famous one. And that makes them operators and leads to the whole quantum formalism. And in that formalism, we can derive the Heisenberg uncertainty relations. Not an add-on, they're things that have to hold once you have commutation relations. Okay, and that says the uncertainty in position times the uncertainty in momentum cannot be less than h bar over 2. So suppose I wanted something that saturated this, that looked as classical as possible, that was allowed by the uncertainty relations. Well, it's a Gaussian. Okay? If I have a wave function that looks like this, then both the uncertainty in position and the uncertainty in momentum are the square root of h bar over 2, and that's the least it can be, and it's symmetric between position and momentum. So in quantum particles, that's the wave function for a particle that looks sort of as classical as possible. And for instance, if you look at Wallace's book, it's things like this are what are going to be appearing in the worlds at the point where you actually have particles. They're going to be Gaussians. Okay, so there's that idea. So I'll call this psi c for classical. That's the wave function. Gaussian. I'll draw the picture. It's the dotted line. That's what it looks like. It's the bell shape. If you don't know, what we have here, A tells you, so x is the variable, we're plotting it in x space. A tells you where the center of the thing is. In this case, I put it at 0, so it's A equals 0. And then the square root, twice the square root of this, of the denominator, tells you what the width is. The square root of half the denominator tells you what the width is. So that's what that number is. It's the width of this. Okay. So we're going to fix on that as being how to think about a classical state. And when we get to field theory, we want the field theory analog of this. And the crucial features are, well, that there's an x squared up it. It's e to the minus x squared. That's the thing you're kind of looking for a Gaussian. And that's what we're going to see. Okay. I probably should have done this one in red. We can define a new operator in terms of the x and p. Here it is. If you haven't seen it before, don't worry about it too much. If you've taken a quantum course, you're very likely to have seen it because this is a very standard thing. But these commutation relations and this definition imply these commutation relations, and then we call these ladder operators. So I just want to explain. So we can define a new operator as their product, and this operator defines the number basis. The eigenstates of the n operator can be labeled 0, 1, 2 and so on by natural numbers in this way. And in relation to the A and the A dagger, if I take one of these states, one of the n eigens, the number operator eigenstates, one of the number states, and hit it with A, I go down one level to the n minus 1 state. If I hit it with the Hermitian conjugate, I go up one. So these three things go together. I have these states that are labeled 0, 1, 2, 3, 4. If I hit a state with A, I go down the ladder. If I hit with A dagger, I go up the ladder. And then these numbers are just for normalization. Just think of the ladder and going up and down. That's kind of the key idea. If you have done the quantum course, then you probably did the harmonic oscillator, this potential in yellow, and what you find is these eigenstates are also the eigenstates of energy, which is what we're interested in finding, and so this is the technique for finding the energy levels for the simple harmonic oscillator. However, nothing I've said here depends on that. So whatever the potential is, whatever the Hamiltonian is, I can have raising and lowering operators, and this gives me a basis for the states. Okay? So we don't have, the harmonic oscillators will be in the background, but I'm generally not assuming that here. It's just a fact that the space of particle wave functions can be written in this number basis. That's what is important for us. Okay. There are going to be some more equations, but I'm going to let you off the hook a bit. If you see a part of an equation in red, I partly did it to make it more readable, but I also did it so you can just ignore it today. And it's in the slides, so they sent around. So don't worry about that. The key thing I want to say is, if I take this Gaussian classical state, and I hit it with an annihilation operator, and I know how to write that in terms of x and p's by inverting this definition, what you find is this classical state is an eigenstate of the annihilation operator, the thing that takes you down, and in fact the eigenvalue is the location of the Gaussian. Okay, so that's the key fact that I wanted to say. Take one of the Gaussian states, hit it with an annihilation operator, it's an eigenstate, and the eigenvalue, the thing is the position that it's located, that the Gaussian, on which the Gaussian is centered. Okay, I'm going to find another state which has the same eigenvalue, but now written in terms of the number operator. I'm going to hit it, so I'm going to hit with the annihilation operator, but the state I'm going to hit it with is this exponentiated, this e to the creation operator. This red bit, ignore it, just tells you how to what the exponentiation means. What this state here really is, that you can think of as just shorthand for this state. And what this says is, the state I'm thinking about is the sum of the n equals 0 state, plus the n equals 1 state, plus the n equals 3 state, all the way to infinity. So this is a state in which I've got a superposition of every single one of these number states. And then there's some weights here to make it kind of work out. Okay? So when I was sort of here, you were just thinking there's one state and I'm kind of going up and down. But I could take two that had different n and add them together, or I could take three, or I could take infinitely many. And that's what this is, this kind of state is called, is about. And blah, 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 some more steps. You find out, well, whatever this alpha, which is just a number I put in here, what I end up with is this state, the thing to the right of the sum, is again an eigenstate of the annihilation operator, except this is the this alpha is the eigenvalue. Okay, so the quasi-classical state is an eigenstate with eigenvalue A. This thing here is an eigenstate with eigenvalue alpha. These are just the same states. A is alpha. This is just the same state in different representations. This one's written in the number basis. It tells me how to put number states together to find these states. And this is written in the usual wave function x basis. They're just the same state written different ways. So a state like this, if I rewrite it in terms of a wave function in space, it is a Gaussian. These are the same state expressed differently. Okay? So this gives us two ways of thinking about these states. We'll call them coherent states. Often people, when they talk about coherent states, it's because they're thinking about it in this sum over many n's. The best way to define it is as an eigenstate of the annihilation operator. That's what the coherent states are. In this, I don't know if I said it here, number or Fock basis, they look like this. In the wave function basis, they look like Gaussians. So those are the states. And that's sort of the key idea. And yeah, now just coming back to this, what I've drawn here is the n, this Gaussian that I drew here, turns out to be the n equals 0 state. Okay. This is that in position space, that's what the number state with eigenvalue 0 looks like. Okay. All right. So we can take so this is the HW is the book. Classical field can be expanded into plane waves in this way. I've summed from, well, we've gone from 0 to what? From 1 to infinity, which is why, even though this is real valued, I have complex valued coefficients here. But what I'm doing is I've got some kind of field, I'm going to break it down into a bunch of waves. Some that have very long wavelength, some that have very short wavelength, every kind of wavelength. And that's what I'm doing here, because these e to the i's are just waves. I'm kind of summing, I can write this as a Fourier sum, and that's what it looks like. Okay. I can quantize, which means this now has to be an operator. And what do I end up with? That means quantizing these coefficients. And the bit I won't show, before we had the XP commutation relations, gave us ladder operator commutation relations for A and A dagger. In this case, it's the canonical commutation relations for the fields. Tell us the same thing. So now we look at this, and what we see is, basically I've now got sort of operators here, so what my states are going to look like is I'm going to, for each k, for each kind of wavelength, I get not a continuous possible amplitude, I just get discrete amplitudes. So these waves that are making up the field don't come in sort of arbitrary amplitudes anymore. They just come in discrete amplitudes, and I have to tell you sort of how many of them there are for each wavelength. And that's what the quantum field looks like. Okay? That's what we get from these things turning out to be ladder operators. So now if we want a coherent quasi-classical state for the field, now what I have to do is, before I just had one number operator and that's just sort of going up and down. Now I have k indices and I'm summing over k, so there's a number operator for every possible wavelength. And so I have to put every one of those wavelengths into a coherent state, and that's what this state then looks like. This infinite tensor product just says for each of the k's, for each wavelength, form a coherent state, and that's what this is doing. So each of the modes is now in a maximally classical state by a previous reasoning if it were a particle. But now I have sort of infinitely many of those, and I'm sort of adding those up together. Blah, blah, blah. The operator changes a bit to this, but if I do the coherent state, it really is an eigenstate again. This is now a field annihilation operator that takes into account all the mode number operators. This now is the eigenvalue, which you'll recognize as this part of the classical field. So this state is picking out this classical field very quickly. Yeah?
Sorry, why are you tensoring again? I thought that the vacuum is already in the Fock space. What is the tensor product doing?
Let's do that. Ask me again. I don't think that's... So this corresponds to the number basis, and we call this the Fock representation, where we're sort of exciting everything into coherent states. So that stands in analogy to the number basis. We now need the wave function sort of picture. People call this the Schrödinger picture of quantum fields. And now we write the states as wave functionals. So x is your spatial coordinate. Phi is then a function, it's a field that lives on that space. And what this is saying, it's a wave functional, it's for each one of those functions, I get a number which is going to be treated as the quantum amplitude. So if I square that, if I take the mod squared of that, what I'm getting by the Born rule is the probability that I'll find the field in this classical configuration. So this is a function of functions, maps functions, namely fields, onto numbers, and so we call it a wave functional. So this is another picture of quantum field theory. And, okay, another picture. Anyway, beginning a few equations. Here's a state. It corresponds, in fact, to this state. To this state, to the coherent state. Writing very schematically, but look, we have an e, so it's an exponential, to the minus, and we have, forget about the alphas for a second, we have something that's quadratic in phi's. So it's a phi squared kind of thing, e to the minus phi squared. So this is a Gaussian with respect to classical fields. This alpha is actually playing, before we had x minus a, which was displacing our Gaussian where we wanted on the number line. This alpha is another field, and by putting this here, we can move the Gaussian around the space of possible classical fields. So we get a Gaussian, so it's as classical as possible, and this alpha tells us where it's centered, so it tells us which classical field is being approximated. This equation, you'll notice, is non-local. It involves two integrals. I'm always going to be taking a field here and a field here and multiplying them together, so they're seeing each other at a distance. This x minus y there at a distance. If you don't have the alphas, we still have that feature, and what this reflects is the non-locality that's just built into the vacuum in quantum field theory. So this is totally quantum. But again, this is again a displaced Gaussian. A Gaussian because it's e to the minus phi squared, and then we've got this displacement the same as before. So you sort of have to picture a space, each point of which represents a whole classical field, and this wave functional is a Gaussian on that sort of can be moved where I want. Yeah?
Sorry, I really didn't understand how you went from the field coherent state to the successive equation in which you evaluate the eigenstate-eigenvalue relation. We got lost there.
So from here to here?
Yeah.
So look at the notes to do to check the calculation.
Okay.
But I'm drawing the analogy to the particle case, where if I hit it with the annihilation operator, it's an eigenstate, and the eigenvalue tells me where it actually is located. Same thing here. I've got this. It's still an annihilation operator, but I have to kind of take into account all of the modes. Again, it's an eigenstate. This is an operator. This is just a number. So this thing here is the eigenstate.
The eigenvalue.
The eigenvalue.
Yeah.
And it's the positive frequency part of this. So knowing this is effectively telling me where the field is, what the classical field is that this Gaussian is approximating. Right? My notation's gone a bit screwy here because down here, alpha x, that's the field that it's centered on, the classical field, and so that's what's being approximated. So my notation, and I'm treating phi as a variable here, so there's a bit of a funny thing. But this alpha x would be the positive frequency part of alpha x. It tells you that eigenvalue is telling you where the Gaussian is. Just an analogy to particles. So you can have the particle, in a way you can sort of throw away the maths and just have the particle picture now, just shifting Gaussians up along a line that represents all the different possible classical fields. And I kind of put a picture of what this looks like, although you can pretend it's a wave function, and these are the classical fields. In fact, it's a Wigner function, but don't worry about that if you don't know what that means. Okay, that's the thing I just sort of said. So things are working the same. If I create something that's a coherent state of every single mode, then what I'm getting is indeed in the Schrodinger picture a wave functional that's a Gaussian that's sitting on top of the field that I was trying to create. So the correspondence between numbers and particle Gaussians and Fock coherent states and wave functional Gaussians, the analogy is the same. Okay, so just as for the particles, a state written this way, state written this way are the same coherent state. Okay. And, okay. I'm sorry, it's going to be too long.
Yeah, you're talking for 40 minutes.
Which, that was 40 minutes, right?
Yeah, you have a lot of slides.
It's okay. I mean, I say it's okay. That's the little physics primer that you need. Now, there's a bunch of equations here. They're all basically pictures. It's a Gaussian. You can see it's phi, e to the minus phi squared. So it's a Gaussian. You need to look at and see here. But the logic is just the same. I can check these are the same states just by seeing that they're the same. That they have the same eigenstates of this operator. So there's this correspondence. And this is useful because one of the examples talks about coherent states in the Fock representation, so it looks like this. The other does it in the Schrödinger picture, so they look like this. So that's why I've kind of gone through this. Plus, if you're going to think about this, these are the key bits of sort of physics that you have to have in mind. Okay. So, de Sitter spacetime. So this is sort of spacetime generalization of hyperbolic geometry. There's this very interesting work by Geneva and various collaborators that I'm going to be drawing on here. So it is sort of assumed in the background independence argument in string theory that you could do the scattering, and string theory is ultimately the things you calculate as scattering amplitudes. And normally you do it in Minkowski spacetime because then it's much nicer. But for instance, people think, I could have just picked a different background and done, fiddled around with the coherent states and done it in de Sitter spacetime instead, and it would be the same. They have arguments that that's not true. You really can't do scattering theory properly in de Sitter spacetime, that the asymptotic in and out states aren't really defined properly, so this really doesn't kind of work. So this seems to be a blow against background independence. So if you want to actually calculate what happens when you scatter in de Sitter spacetime, you're going to have to keep it in Minkowski spacetime. And the only thing that you can obviously do is try to create a de Sitter geometry using a coherent state in Minkowski. Because then you can do the scattering, because it was really all sort of happening in Minkowski spacetime with this coherent state. That's the sort of program. So we need a coherent state in Minkowski spacetime. There are some complications to the coherent state story that I told you when you come to massless spin fields. So actually you can't quite do the thing that I did exactly. There are complications. But what you can do is those complications go away if you give your gravitons a little bit of mass. So they don't propagate forever. This is a sort of trick. There's a way to do it where you don't do that, where you use BRST quantization and things get a little more kind of hairy. But I'll talk about this paper. If you actually want to be able to construct this coherent state, you have to pretend that the gravitons have a little bit of mass.
So what does this finite pitch mean?
So I will come to that, but what I mean is, one of the ways you can... ask me again. If I don't answer that question by the end of the slide, I'll come back to it. Well, I wrote this down, but you can see now it's a coherent state. It's like one of these sums over every value of n. So that's definitely a picture. This is the sort of equation at the center of their paper. That's what the state looks like, and it's really reduced the degrees of freedom of H, that sort of perturbing metric, down to 1 degree of freedom, and then that's what you see as a coherent state. In some sense, the whole discussion of number operators and Fock space was so you can look at this and you'll say, that's a coherent state. Now you know what it is, okay? So that's what you will recognize, and it is.
So is lambda is a kind of not the cosmological constant?
It is the cosmological constant. Thank you.
Okay.
Which is something like, but the mass is this gravitation. Yeah, the graviton mass is also kind of a function of this.
Okay.
So it does, yeah. So it's not so surprising that it shows up. Well, I mean, it's not so surprising, right? I mean, what your de Sitter geometry is depends on how strong the cosmological constant is. That's what you're sort of seeing here. Okay, all right. I'm going to say the interesting things now. So if you were kind of getting at all lost in the actual sort of equations, here's the fun parts that I want to kind of talk. So one thing they show is if n goes to infinity, this does reduce to semi-classical gravity in the sense that I said. Here's one of the things I really want to sort of focus on here. So think about measuring the length of an interval. So suppose you have some nice clock, and you send it along its world line, and usually think of this as an odometer. It kind of ticks off units of interval, and length of the interval is going to be whatever you start the clock at 0, and then whatever the clock reads at the end, that's the length of the interval, because it's been faithfully ticking away, measuring how long that curve is. Okay? That's not what's going on here, because the space-time, the actual interval along the curve in this picture is given by the Minkowski metric, the background, and not the de Sitter metric. And the reason the clock says what it does at the end is not because the curve has sort of got longer, as it were, comparing the two. It's because the clock has slowed down. Okay? So there's the same effect, this redshift effect in this picture. The clock's measuring the Minkowski geometry, which is different from the de Sitter geometry, yet these two pictures have to be equivalent. What actually you find in this theory is that there's stimulated graviton emission, like electromagnetic stimulated emission. Your clock will radiate a graviton and slow down. That's the whole process here. So I want you to think about that, because we're going to see that again. And this was about the patch. One of the things that they want to do this calculation for is to actually do a calculation of how long the thing will stay in a coherent state. The equations are non-linear. That means if it starts in a coherent state, it won't stay there forever. And the fact that it doesn't stay there forever is one of the arguments for why you can't really do scattering in de Sitter. You can't really have an infinite de Sitter background. This was a question we asked in the book and didn't really sort of answer. So there is kind of an answer to this. Okay. Another example with some similar kinds of lessons where we're doing something different. That was about trying to construct de Sitter space-time in Minkowski space-time. I will just remind you of the time-dependent and time-independent Schrödinger equations. The time-independent Schrödinger equation relates the rate of change of the wave function to the Hamiltonian. The independent one is really the eigenstate equation for the Hamiltonian. But you put these together, if you have a state that's an eigenstate, then this is the solution to the time-dependent Schrödinger equation. There's an initial state, and then this phase that depends on the energy. But what you notice it is, the greater the energy, the longer, the slower it takes to go, the longer it takes to go around. okay? That the phase depends on the energy. And so if you have two functions of different energies, they will have different phases, and if they start in sync, they will get out of sync. So, this was a book I wrote with Niels and Mike Schneider. Flea egg, kind of gross, but it's sort of nice because it also has the property of basically having the Planck mass. And so what one's interested in doing is taking two, they won't use flea eggs, but that would be the sort of idea. Take a pair of flea eggs, this is around the Planck mass, so maybe they're quantum, try and put them into space, both into spatial superposition, but they're quite big, so they should have a gravitational effect. If I do this, then effectively I have a superposition of two that are on the left, two that are on the right, a left right and a right left, namely this state. But now, the ones where they're like this, which I guess is right left to you, they're much closer together than the ones, say, when they're here, which is left right, that one's right left to you. And so there'll be a different gravitational potential energy. There will be different phases associated with these terms depending on how far they are away. If they start out in sync, they end up. But there was the picture. We get different phases, and I'm pretty sure that's an equation you don't need to read. You can see the different phases here. But they start off like this. They pick up, each term picks up a different phase, and we go from a state that's not entangled between the two to one that is entangled between the two, and that's something that can be measured. And this is purely a result of their gravitational interaction. So this is a measurement that depends on there sort of being a gravitational superposition and is observable. Semi-classical gravity says there should not be any such entanglement. Gravity stays classical, and so people are trying hard to actually to do the experiment to measure this. And people who are trying to observe it obviously expect to see that this is actually going to happen, and that this is a gravitational effect, an effect of quantum gravity, because semi-classical gravity, where gravity is just classical, does not predict this entanglement, whereas if you treat gravity quantum mechanically, you do predict it. Okay, there's some arguments in the background about whether this really is a proper quantum effect, but the bottom line is, if you were thinking of gravity as itself an independent system in here, so really I've got the two grav cats, and I've got the gravitational field and something that's going on there. If I see the entanglement, then the thing is quantized. Okay, and then you can read about this in another nice book.
It's a horrible color, right?
With a, yeah, don't judge this one. Don't do that. Okay, nearly there. So that's sort of the physics background. I want to emphasize that what's going on in that calculation is I have gravity, and they're in states of gravity, they're in a quantum superposition. So how should I think about this a bit less naively? Christodoulou and Ravelli had a very nice way of thinking about this. Each one of those, we'll sort of do it in GR, so each one of those pairs, those four pairs, corresponds to a different geometry from a GR point of view. Everything's light, everything's moving slowly, so, I mean, they're just point masses, so it's Schwarzschild-like, but it's all slow, so it's non-relativistic, and this is the Newtonian approximation to Schwarzschild. And then the way you calculate it is, it's no longer sitting in the same space-time. When you have to think, well, I've got one source here, what's happening to the other one? In some of the, so I've got one source that's curving geometry like this. Where's my other one? In the state where it's near, it sees more curvature, and so it'll take a path of one length. In another term in my superposition, it's out here, and space is basically flat. It'll take a different length path. So I have clocks that tick regularly. The rate at which they tick depends on their mass energy. That's what gives me the phase. And the reason the things get out of phase is they're traveling along different length paths, and so they measure different amounts of time. That's the picture that they have. And another, sort of okay picture. This was a thing I wrote with Carlo about these experiments recently. Sorry for all the plugging, but anyway. But what they just assumed that it was okay to say, oh, quantum state that's like this, quantum state with the thing that's like this, but in another place, and I can take quantum superpositions. But this is all very just sort of ansatz-y. I'm just going to do this. And if one wants to really see that this makes proper sense, put it into a more rigorous framework, well, we need to go to quantized linear gravity. We need to construct the coherent states. Because if I can now have my coherent states, they're in a quantum theory, we know we can take quantum superpositions of them. We want to see that done. And recently, Chen, Giacomini, and Ravelli did just this. So what you do is take Minkowski spacetime, they work in the Schrödinger picture, wave functionals, and construct the quantum states for these Newtonian solutions, show how that's done, what they look like, take superpositions of them, and you get solutions that look like this. Another picture, but by now you all know how to read this. It's done in momentum space, so there's one difference. But again, here's my H field. I've got e to the minus, and I've got h squared. Again, this is a Gaussian state. This k here is in this representation, the 1 over x minus y squared part for the non-locality. I just wrote this just written in a different way. We have this delta function, which is really in gauge terms it's the Gauss constraint, but what it's really saying is Newton's law has to hold. This is saying that you have to have a Newtonian potential. That's what this part's doing. And this is part of the funniness of trying to construct these states out of massless spin fields. You end up with this enforcing that it really is the Newtonian solution. But it's Gaussian. I did the ground state, so there's no shifting here, so this is a bit of a funny one. Okay, you can then put in different fields for different kind of mass. This rho is the mass density. That's the thing that's depending on this. And then the energy that you get above above the vacuum, that's identified with the Newtonian gravitational potential energies. These are now quantum states, so we know we can superpose those. That was kind of the point of the exercise. These coherent states, there's no gravitons being emitted here because we're doing coherent states, so I have a sort of question about how Penrose would how you would make out that. This was the point I wanted to come to. In this story we had fixed clocks measuring parts of different lengths. In this picture, we've gone back again to Minkowski spacetime. So they're traversing paths of the same length. Everything's moving the same length path. And now in this picture, the clocks have slowed down. That's the effect because there's this energy difference here. So it's the same as before. Why are we getting this interference in both sources? In this story, it's not up here. We have fixed clocks traveling different length paths. Equivalently, in this picture, same length paths and the clocks are changing time. Okay. So, yeah. So this was about constructing classical spacetimes in a Fock and Schrödinger kind of way. So this is what you need, the framework you need to think about if you want to think in general about a classical limit of quantum field theory. In this case, applying it to gravity. How do we get to a coherent state? How long do we stay there are some of the questions. This helps us probe what it's like, what it means for geometry to be quantum. And it raised some issues of background independence. I think this is something that's kind of pretty cool to think about, and actually, when you think about it, is what must be happening in this picture. I have to stop. But it's really seen it explicitly. What's going on when we see things getting out of phase? Do we have two things traveling paths of different lengths, two identical clocks, or do we have two different clocks traveling paths of the same length? Honestly, the natural thing to say is that that's just equivalent descriptions, and one should not take this split between gravity and the perturbative part of the geometry and the perturbative part seriously. This is, I was sitting here, the one thing I was going to do was have Poincaré kind of appear in a ghostly fashion here. This really is a sort of quantum gravity version of the heated plate for Poincaré, but these things really should be the same. But you can really see it worked out here. And so there's the hodometer for measuring the distance of the paths. Those of us who've been in the orbit of Harvey Brown will kind of appreciate this kind of stuff. That these are equivalent, but seemingly very different, on face of it, very different descriptions that are equivalent is actually a pretty common view amongst physicists. And you might think, yeah, string theory is quantum field theory. There's a whole chapter of Thorne's popular book where he argues for exactly that point that I think is sort of good to put here. And I think it's not something that occurred to me before, but I think philosophers have talked about before. But I think it should be taken seriously. And there we go. And now I'm glad we called it at the Planck scale, because we wanted to call it philosophy at the Planck length, but now it does still include the grav cats, because that's not at the Planck length, but it is at the Planck scale, and I think it was Carlo who told us that we should do that. So he was being prescient there. So thank you, and sorry. Yeah, okay. Last time I gave it, I had 20 minutes for the talk. So.
Thank you very much, Nick. That was incredible pedagogical. I've learned a lot from it. First comment I want to make is a suggestion, maybe instead of rabbit cats, maybe rabbit flies, because we lay eggs and flies with rabbit But, so can I use this?
Yes. But don't use those pens. These two pens are...
Those are the whiteboard markers. Apparently the one I wrote was not.
Okay. Okay, the way I will structure my comment is following the order of the presentation. And this is just a schematic way of doing things. So, first I'll talk about the order of quantized linear gravity. Okay, and the first, so just to, I'll pose some questions later, but so quantized linear gravity, as Nick showed, this is a low energy effective theory, and is as seen as the goal for any quantized theory of gravity. We want to reach at least what this theory is saying to us, but should be understood as an effective theory, and we use this, as Nick showed, as a perturbative approach to the quantization of gravity, and so we treat this in a perturbation theory and use the methods of quantum field theory to find a Lagrangian there, and we impose the canonical quantizations, canonical commutations, and then we have the graphs. So this is very similar to quantizing the electromagnetic fields. In a bosonic theory, you get the photons from this, massless photons. And since this is an effective theory, it should be understood as such. So a negative point I would say that it's presupposed in Minkowski spacetime rather than deriving it. So in quantum gravity, we want to derive spacetime. We don't want to assume it, and this is not a theory, a proper theory of in the end for all the range of quantum gravity. But this positive aspect of it, as in quantum field theory, is that it justifies why the graviton must be a spin to boson. So it describes this in this domain gravitational waves. So we want to reach that. So now my comment, because this was just an exposition, of course, and Nick said that better than me. So my first comment is that how should we understand these gravitons? That we reached these gravitons and we started from string theory. At least that's the background, and Nick told us that not really focus on the background, but I wanted to focus a bit because we were interested in connecting the two things. So focusing in string theory, there the gravitons, they are the excitations of strings, they are modes of the strings. And here in quantum linear gravity, these are just derived from the fields, as in quantum field theory. So how should we connect, how should we make this correspondence that Nick told us that we should do, we should understand? How should we understand this correspondence between the gravitons of string theory and the gravitons of this effective description? So the first point that here I want to mark is this. I would say that these gravitons of this effective field theory, I would call it is an effective ontology. This is the graviton that, again, how should we understand? Maybe we should look at the graviton of string theory and try to respond to that. So that's what I'm saying. It's an effective ontology. And maybe a little comment in string theory, why I'm also posting this, focusing on this background, is that I think since we are searching for this correspondence, and this is also, and in quantum linear gravity is similar to other quantum field theories, that we also quantize the field and we get other particles, like photons, like the particles of the standard model. Should we also understand these other particles as effective ontologies that we want to recover from a more fundamental zero, let's say? And in this sense, a theory of quantum gravity, should that also involve this ontology, should also derive this ontology, in the same sense that in string theory we can talk about the gravitons that are there, and also string theory we can also talk about the other particles. The particles, like electron, is also in string theory, and we could make this correspondence in string theory, but other approaches of quantum gravity. It's not included. Other particles are not included. So I'm just pointing out to string theory, to this background. Maybe this correspondence has some privilege. String theory maybe stands out as other approaches. Okay. That second point would be coherent state. That's central to the presentation. So, and it presents us with coherent states in terms of particles and fields, and the states which are the eigenstates of the annihilation operator. They minimize uncertainty principle. They are responsible for making the connection with the classical description. So particles and also for fields. And right, in short, I would add to this that coherent states reproduce quasi-classical behavior, but they may be. So the question is this really the whole story? Shouldn't we also involve other methods? Is this classical limit can be just the analysis of this can just be also in terms of the coherence states? Should we also not involve the coherence or maybe the measurement problem? And maybe that's not part of what Nick wanted to present, but I think these are things that at least at start, and to give a big picture, a complete picture, should we also involve the coherence and measurement problem? And just for the fitness of coherent space also should apply for the zeta spacetime. But here, and here, when we go back to the description, because we want to recover the field and the zeta spacetime, are we back to an effective description of a field? Because this is a field, and that the gravitons again, this state is coherent. This coherent state. Are we back to the same story of how we were in the field, in the effective field theory? How should we understand this connection between from the graviton, from the states of coherent gravitons recovering the field? Is this still and is this also an effective description? And that's the main worry I have. I would say here, this side, this side. So effective. And what if gravitons are massless? Because if you consider gravitons with mass as massive, but what if they are not? Can we? That would affect the equation, and can we also deal with that? And first, to finish, as to 10 minutes. So the address spacetime. I will quote your Nick's work with Chris. That you say that the metric field is taken to be a coherent state of string gravitons. So stress in string should that be string. If space-time is to be understood in terms of coherent states, what does the world look like if in a general state that's not coherent? Because since the geometry of general relativity is recovered from this coherent state, that's just a sufficient condition. But what if we are not in a coherent state? And this could be just. What if we just consider if the equations are actually non-linear, because then you will have also there's another I would say that applies only for if the equations are linear. So if we include interactions, if we include that in the equations are non-linear, then would we still have the space-time analysis? Analysis of course applies for this case. So that's what I would say. So I would call this a non-coherent universe. What is that? Does that include space, system, and coherent? And that's actually all I have to say.
So let me be really brief since I really took up a bit too much time. So anyway, thank you. I want to say that these are great questions, especially since you just had my slides to work from, and then they ate into your time, and so this was really great. And I'll do 2, 3, 4 because I think they're most of the point would sort of come up on the end. And yeah, I mean I really like all the questions that you sort of asked here, and in some sense I would sort of roll them into this general question about classical limit of QFT. I think most of them, measurement problem, how do we get these states, what's happening when we kind of perturb in other ways. I think, yeah, absolutely, I really like the things you're kind of asking here. And in some sense, yeah, someone should write a dissertation about it, probably. What I was trying to do, obviously what I was trying to do here was just kind of give the framework where one can start to sort of address those questions, but I think they're really kind of key. Is that okay? Well, if I have some answers for some of them, we can talk a bit more. I do think I have another project which is a bit to do with how this question of how you get to a coherent state in the first place, and obviously that here how long you stay in a coherent state is part of this, And this, I'm interested in this for fields because it's quite well understood for decoherent. There's a decoherent story about this for particles, but it's not really worked out for fields. So that's, yeah.
Maybe you could comment about the non-coherence universe. Do you think that's a possibility, an option? If we don't have the gravitons, they're not in a coherent state.
So yeah, sure. I mean that's sorry. So in the Diwali kind of case with the sitter, that's exactly what happens after this quantum break time. They just stop being in a coherent state anymore. But you got to remember the thing's time symmetric as well. So had to be kind of been there forever either. You know, this works at both ends. But had to have got there somehow as well. In some sense, maybe this is connected to you're just getting away from classical gravity. There's sort of a regime where it's quantum. It's not classical at all. Yeah.
All right, so we're going to take 15 minutes for the questions. I think that's roughly okay. We still have plenty of time for the buffet in this building. Yes, so Elisa, then Niels, then Enrico, and maybe someone. Okay.
I'm having a hard time reconciling the claim that this is a quantum theory where you get the classical space-time out of some kind of coherent superposition with your picture of the Gaussians. So I want to understand this better. Like, this is a quantum theory of space-time that you have, I mean, there are no hidden variables or no collapses. You haven't said anything like that. So I'm assuming it's ever-ending quantum mechanics. By ever-ending quantum mechanics, I just mean no collapses, no hidden variables. And usually when we're talking about coherent superpositions, you've got, or coherent states, right? You've got multiple things. Now we want some kind of determinate, classical-looking space-time, but isn't it, then the quantum state isn't like a Gaussian around this classical space-time. You're going to have like multiple, unless there are some collapses, aren't there going to be multiple classical space-times? And we've got a coherent superposition of those, or am I'm totally confused. Is there just one classical space-time, or when I hear coherent state, I'm thinking coherent superposition, and so I'm thinking multiple classical-looking things.
So there's a fundamental ambiguity. So
yeah.
Coherent in this sense is not the opposite of decoherent in a sense of decoherence.
Okay, good.
So
We're
there's
getting
two senses of coherence that are at play here.
But you haven't said
So
anything about
fundamentally-
collapses or hidden variables, so I'm thinking you do think there are multiple classical spacetimes, right?
So the whole, yes. So and then right, this is what I was talking about as well. To really get a classical limit, there's a lot more kind of work to be done here. But this is just the intuition. Like, the thing's still got to be in a quantum. After collapses, whatever, decoherence, it's still in a quantum state. It's not going to be, particles are not going to be perfectly localized if it's unitary, right? So what states must we be talking about? And then it is these Gaussians that are as narrow as possible. If you look at Wallace's book, this is really the story he tells about particles. There's a discussion about whether this is enough to just put things in coherent states, and that's how we recover classicality. But then there's a discussion that kind of doesn't do the timescales well enough. But ultimately, those are the quantum states that we want, and there's a discussion of how decoherence will drive things basically into these kinds of quasi-classical
Oh,
states.
okay. So when you talk about a Gaussian, you're ignoring like other parts of the whatever phase space or whatever.
So if I want to think, how does quantum mechanics represent a particle that's effectively localized? Yeah. by a Gaussian. I mean, I'm ignoring it because it's 0, you know, it's this close. It's very close to 0 everywhere else except where it's peaked. So there's another question about if you were really going to do this through, what you would hope, you know, you would expect there to be branches where it would be a superposition of different localized passing. And what to do about that is just another question. The question here is about what are the states that are getting superposed that could even be called classical in the first place.
Thank you. Okay.
That's the picture
Yeah,
here. Does that make sense?
Yes, thank you.
And really, what you don't want to, in the sort of ever a picture, you sort of start with a superposition of these two things, and what you want is decoherence to sort of make it into a mixture of these two things rather than. But that's all kind of downstream and other kind of. What are the even states we should be talking about in the first place?
Thank you.
Good. Sorry. Yeah.
Thank you.
Yeah.
Yeah, thank you very much. I'm wondering how far your low energy gravity conventionalism goes. So for instance, in this Wallace paper you cited, right? He defined somehow formally low energy gravity is somehow just by a path integral, which is to be understood non-perturbatively. And then you can kind of probe this with different approaches, for instance, perturbative quantization around the linearized background, or stochastic gravity, and so on, right? And so I understand kind of in the perturbative way of working that you might want to say, oh, I can switch between, let's say, Minkowski background and a CT background, let's say naturally asymmetric series that's somehow linked to Minkowski, or maybe holography, I don't know, maybe this is a speculation, something holographic maybe to RDS or something, you know, and so on. But then this all kind of seem to be different, so to speak, patches of the overall elephant low energy gravity as kind of formally yet imprecisely and not really well spelled out path integral formulation of low energy gravity as, for instance, put forward suggested by Wallace. So in that sense, I don't really see that one necessarily has to kind of say that this regime, we have conventionalism, it's really, we have different ways to look at the overall thing. Yeah, I'm just wondering what you make of this picture.
So I'm not sure I totally get the general scheme that you're fitting this
the elephant,
sort of into.
The elephant, right, is this, I mean, this elephant is this formally defined path integral low energy gravity, and you look in your trunk and your feet you're looking in, and this is like Licita and Minkowski, but there's also the stochastic gravity approach and so on and so forth,
Yeah, I don't know. I guess I will stay neutral on that for here. I mean, for me, I kind of given you, when I realized what was going on and started thinking about it, I was quite surprised, and I think, although in hindsight it was kind of clear that this sort of thing must be going on. These are quite, I'm only making the claim or pointing to a couple of cases in quite a limited domain here that you're going to get the same physics,
right?
And one way and it's just a perspective, whether it's constant clocks and changing intervals, changing geometry or fixed geometry and changing clocks, that those really are the same thing. Yeah, I mean, maybe I have sort of imperialist kind of ambitions to spread it out to other things, but I don't know.
Yeah, okay.
Not really, because we were talking about this the other day.
Yeah, but this is a new image, I think. You can just expand this a bit more what you're looking at, and then you get this, I think, more holistic. But anyway, picture.
So, anyways, does that kind of...
Yeah, I think so, yeah. This helps.
Yeah, I think that this is one of the very long list of questions that in the interest of time will just reduce to the most generic one, so we can take up as much time as we can. I was kind of curious. No, let me put it this way. I was kind of curious. This is going to be the most logical passing I can think of, because it basically goes back to your point one, and somehow I think it connects with the other ones, which is the following. How much of what's happening in most of these examples and what goes in the background of this entire discussion is to some extent an artifact of, not an artifact, but a consequence of the symmetries of the background. Because, and let me explain why I'm saying this, otherwise it seems very random. There is a very old problem in mathematical relativity from the 60s that's become relevant in holography recently, that's why I know about it, called the linearization stability problem, which basically asks the question of when a linearized solution to the Einstein field equation approximates an actual solution and when it does not. And a very old result from the 60s basically says that you can always do this if your background breaks all the symmetries of the theory. You don't have any isometries left. And there are sort of tricks and things that one can do to sort of show that something very similar applies once you start doing perturbation theory in H-bar, so it should apply to your regime. And this sort of led me to think that, for example, a lot of the trouble that there seems to be here with like the De Sitter solution, in writing down a scattering theory for the De Sitter solution, might ultimately come out of this. So the De Sitter vacuum spacetime in which I think you are working effectively has a lot of isometries. And it makes a lot of sense that introducing a massive graviton would save your scattering theory, because a massive graviton breaks basically every symmetry you can throw into the theory. So I was sort of, and I'm pretty sure you can do some trick like this for most of the other issues. So I was sort of curious if you had looked into basically how the properties of the background are relevant to a lot of these results that you're getting.
Right, I mean that's a great question. And I know that because we kind of talked about it a little in the book. So. Oh. No, but not actually not the way you asked it, which I think is a very good way to kind of ask it. We talked about in what space times you have the right symmetries to actually kind of, so that the excitations are still gravitons.
Yeah.
So I think that's great. I think my understanding has now kind of has changed a bit. But then I don't quite know how to think about this classically. But you know, when you're constructing this De Sitter coherent state, if you do it with the massive gravitons, or if you do it with the RST way with massless gravitons, you're no longer in. I mean, De Sitter is not a linear approximation classically to Minkowski spacetime. Once you've got the gravitons, you can build up whatever coherent state you have, whatever coherent state you want, and it does not have to then be a linear solution to what you have. So I think the answer is, I don't know how to kind of relate it to the linear stability problem, because I think it takes you it must be doing, there's a different way of thinking about it that takes you can build whatever coherent state you want, and then you can still have, because it's Minkowski background, your perturbations are still Minkowski gravitons to that coherent state. So, yeah, I don't know something kind of rigorous, and we thought about it a bit in another way. Yeah, but that seems to be the picture.
Yeah.
But this will take you beyond.
Yeah, because at the very least you're going to have trouble with the types of perturbations that you can do if you don't have some of these results. So you're going to have trouble with any like compactly supported perturbations if you have a background with too many symmetries. Because you won't be able to get them to satisfy the Einstein field equations because there won't be different variables. But
so then I think this problem then kind of bears on this question of background independence.
Yeah.
The importance that it is Minkowski, or perhaps De Sitter or something that's sitting at the bottom on which you're building. I think that I'm now much less confident in the background independence argument that we gave in the book than I was, I think. But I blame Chris. Yeah.
Oh, good. All right. Well, I have 2 more minutes. So before we start, I just want to make a comment on the citations at the end and to say something a bit more metaphysical. Because you always stop, and you're always very careful not to talk about the metaphysical implications. That's why I really like to.
What was this?
Yeah, but
I'm disappointed that metaphysicians are not complaining about my.
So here's the thing. So right, is spacetime really flat or is it really curved? To a physicist, that's an interesting question, but of course for metaphysicians that's very interesting, right?
Yes.
And I think there are different options, right, depending on how you think of the emergence of space-time. Because, so you could have a view where you say there is no matter of fact, right? That would be something you say about the world. But if you are, say, realist about space-time, I think it's grounded in the non-spatial temporal structure, then there is a question about is it curved or not, right? And perhaps if you're an eliminativist and don't think there is really a spatial temporal structure emerging, then you might think that's the right thing to say, that there is no matter of fact. But you're going a bit further and saying it's not an interesting question. Yes, that's an interesting question, but I'm saying there is no matter of fact about whether space-time is curved or not. Just wanted to say something a bit more metaphysical to this. But yeah, anyway, thanks a lot. Let's thank Nick again.